Okay, so for the quiz tomorrow, the idea is you need to know about domain range, functions, relations, increasing graphs, decreasing graphs, positive, negative, etc. So the term relation, all that is a set of ordered pairs. So a relation is a set of ordered pairs. Remember, ordered pairs are like x comma y. They're just points on a graph. If it's a function is a specific relation in which no x values repeat. So it's a relation in which no x values repeat. So when we talk about independent variables for a function, the independent variable is also known as the domain because the independent variable happens to be the x, or it's graphed along the x-axis. Okay, so if we talk then about a dependent variable, that would be the range, the y values. So they ask for, if you're given this domain, -3, -1, 1, 2, 3, what's the range of the function f of x equals x squared minus x? Remember, what that means, f of x equals x squared minus x, they're telling you that wherever you see an x value, and all of these are different x values, you need to plug in the value for x and evaluate the expression. In other words, when we want to evaluate the function at -3, the actual rule says it's x squared minus x. Well, if I'm evaluating it at -3, that means I stick in a -3 wherever I see an x. Well, -3 squared is 9, and 9 minus -3 becomes 9 plus 3, or that becomes out 12, or what comes out is 12. When we evaluate the rule for f of -1, again, the function says it's going to be x squared minus x. When I plug in a -1 wherever I see the x term, -1 squared is 1. 1 minus -1 becomes 1 plus 1, or 2. When you evaluate the function of f of 1, it becomes 1 squared minus 1. Well, 1 squared is 1. 1 minus 1 is 0. When you evaluate the function of f of 2, it becomes 2 squared minus 2. Whoopsie, this should be... It becomes 2 squared minus 2. 2 squared is 4. 4 minus 2 is 2. And then lastly, when you evaluate the function f of 3, it becomes 3 squared minus 3. 3 squared is 9, and 9 minus 3 is 6. So when it asks you for the range, then basically all you need to do is state it in set notation. The range is specifically the set of the set of y values that came out. So what is the range? The range is 12, 2, 0. We already have the number 2 listed, so there's no need to write it again, and 6. So the range are those specific ordered pairs. Multiple choice. A stands for this relation, which is the ordered pairs of 1, 4, 4, 7, 3, 7, etc. Which of the following statements is not true? The domain of set A. Well, the domain is all the x values. So I do see the x value of 1. I do see the x value of 4. I see 3. I see 5. I see 9. I don't see 7 anywhere. 7 is nowhere in the domain. So my guess, it says which is not true, it's going to have to be this, but I'm just going to double check the others. Is set A a function? Do any x values repeat? See if I can get this thing off. So is set A a function? Well, let's see. X values, none of those x values are repeating, so A is a function. That is true. The range of A, the y values of set A, +4, +7, +9, +2. 7's been written twice. This is the range. And if any set of order pairs is a relation, so this is out. This must be the answer that's not true. There is no 7 anywhere in the domain. We need to graph this function, the absolute value of x minus 2, using a table of values. We need to state the domain and the range. And then we need to use the calculator to help you determine for which values of x you want to use. Well, I don't really know what to use for the values of x. So I'm going to actually go to the graphing calculator. I've already cleared my memory. I've cleared my RAM. I'm going to go into y equals, and I'm going to type in the function that they asked about. It says y equals the absolute value of x subtracted by 2. Well, under math, over to number, ABS is absolute value. I want the absolute value of x. I don't want to be in there anymore. I arrow over, and I want to subtract 2 from that. So I'm looking for the absolute value of x minus 2. If we go and take a look at the graph, we should see a V-shaped graph whose turning point is right down here. That's where that point or the graph goes from decreasing to increasing. So we want to be able to plot those points on a grid. So if we look at the table of values, I should be able to kind of determine where that turning point is. And the turning point to me looks like it's starting at the origin and looks like it's going down about 2. So if that's the case, and all the other points on my table of values are going to be around it, like symmetrical around it. So let's see, second table. I see where that 0, 2 is. Let me arrow up a little bit. And you should notice that when you have your y values matching up on either side of that turning point, you've located the lowest point or the minimum. So it looks like 0, -2 is the minimum. And then I've got these points around it, -1, -1, 1, -1, 2, -2, 0, 2, 0, -3, 1, and 3, 1. So when I kind of get into here, I can now see this V-shaped graph. Those are the points I'm going to use on my table of values. So I'm going to go back to here, and I'm going to say, let's use the -3, the -2, the -1, the turning point at 0, 1, 2, 3, whose f of x or y values, -3 was 1, then -2, 0, -1, -1, 0, -2, 1, -1, 2, 0, 3, 1. So these are the points that I'm going to graph, and then I'm going to make that same exact V-shaped graph that I saw on the calculator. So -3, +1, -2, comma 0, -1, -1, 0, -2, 1, -1, 2, 0, and 3, 1. What we saw on the graph was a shape that looked like this. And it really does go on forever, because I could have kept scrolling up or kept scrolling down. So the domain ends up being that, yes, I chose these specific x values, but if I go back to my table of values, I can have the domain being any value I want. I can keep going in the negatives. I can keep going in the positives. I definitely know that I've got some decimals, right? Because even though these are all whole number pieces, I know that I could go over a little bit more than, let's say, 5, 1, 2, 3, 4, 5, like in a half, and I would find a corresponding y value. Or I could go over to -9.5 and find a corresponding y value. So essentially what happens is my x values can be anything I want. So in terms of the domain, my domain is the set of all x such that x equals the real numbers. I can just get rid of reals. It doesn't really matter. X equals, I'll just put real numbers. So anything that I want for x, I'm allowed to plug in. I can plug in whole numbers. I can plug in fractions. I can plug in decimals. I can plug in pi. Doesn't really make a difference. The range actually is restricted, because if you look at this particular graph, even if you look at the table of values, I'm trying to get a highlighter up here. So this is the lowest possible y value. The graph shoots everywhere up from that bottom point. This vertex, this point right here, happens to be a minimum value. This is the lowest point, or a minimum, because the y's on either side of it keep getting bigger. So what that means in terms of your range is that your range is the set of all y's such that y is greater than or equal to -2. Because y's, even though I'm only showing you some integer values, I could plug in a decimal for x, do the square root of it, minus by 2, and out would come a decimal. So this is going to be your domain and your range for this particular absolute value function. And again, this is an absolute value. And we went to math, and we went over to number, and then we went down to what's called ABS, or the absolute value. Alrighty. Next one. Which value is not in the domain of y equals the square root of x squared minus 4? You can do this one of two ways. You can plug in the values or go right to your calculator and check your table of values. I think that's what I'm going to do. So I'm going to go into my calculator. I'm going to go into my y equals. I'm going to erase this stuff first. So I'm going to go into y equals. I'm going to clear out what's there. In order to find the square root function, I'm going to have to go back to math. The square root function happens to be, actually, I don't even have to go into math. Let me get out of that for a second. I could have gone into math, but the square root function happens to be right where the x squared is. Let's try this again. If I look above the left-hand side, if I do second x squared, that's the square root. And what do I want the square root of? I want it of x to the second power. And I'm staying underneath that square root, and I'm subtracting it by 4. So really, everything is under my square root. I'm going to kind of come out of there, and I see my square root of x squared minus 4. I'm going to go to my graph. Interesting looking graph. We haven't really seen one of these quite yet. But now if I go to the table of values and I find out which value is not in the domain, well, let's see. If I look for the value of 1, if x is 1, well, look at the y value. It's an error. I can't be in the domain there. I don't have an answer. When x is 2, sure enough, I get an answer. The answer is 0. When x is 3, out comes, whoopsie, I don't know how I got all the way down there. All right, let's go back up. I don't know how I got down that so far. But you should have seen, hopefully in your calculator, that as you keep going down, when you look at x being 3, you get an actual value for y. And when you go to x equals 4, you get an actual value for y. So basically what's happening is the only time there is no domain is when your x value ends up being 1. Right? So at 1 we have an error, at 2 we have 0, at 3 we have 2.2, etc., and at 4 we have 3 point something. Well, hopefully that makes a lot of sense, because remember, you can't take the square root of a negative number, and what would happen here is if I evaluated y equals square root of x squared minus 4, when x is 1, under the radical I'd have 1 minus 4. Under the radical I have -3, and we can't take the square root of a negative number. So what value is not in the domain? I can never have x to be 1, because when I square root that expression, I'm going to get a negative, and that doesn't make sense. If we don't want the relation to be a function in number 8, we don't want x values to repeat. You've got a lot of choice to do whatever you want. I could always just easily, bring stuff over like this. But what ends up happening is, for this not to be a function, I could also shoot another arrow off of any one of these x values. I could shoot another arrow off of -3. And now I've got 5 different ordered pairs, in which one of my ordered pairs would look like -3, 1, -1, that's a mapping that I've mapped, and -3, 4. But the fact that I've made x values repeat, I'm not a function. So here's an example of something that's not a function. Okay, so the next one. Graph the function f of x equals the square root of x plus 3 using a table of values. State the domain and the range. Use your calculator to help you determine which values for x you're going to use in the table. So let's go back to the calculator. Let's go back to y equals. and we need to change this square root function to being x plus 3. I'm just going to clear out what's in here, and I'm going to do second x squared, which is the square. That didn't work. Try that again. So I'm going to go to second x squared, which is the square root of underneath that x plus 3. I'm going to come out of my radical. I'm going to go to my graph. I'm going to take a look at this thing here. And then I see that the graph looks like it starts here. That looks like it's over about -3, 0 and kind of continues up and over. So if I go to the table of values, I'm going to be able to find points that allow me to graph this function. As I start looking at the table of values, I want to find out where the error message is. Where's the first value that I can't take the square root of because it's negative? And that would be it. So it looks like points that I could actually graph would be -3, 0 would be easily graphable. -2, 1. 1, 2 would work. And as I go down, I've got like 5 boxes to fill in. Let's see what else makes sense to graph. Decimal, 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 decimal. Aha, 6, 3. That's good. And I've got one more box to fill. Let's see where it's going to be. I keep getting all these decimals, decimals. Oh, there's one right here. 13, 4. So these are all numbers that I would want to graph because they're not decimals and it makes my life easy. But I could keep scrolling down forever and ever and ever and get a whole bunch of different x values. That's going to tell me something about my domain. So as I go back here, I realized the first graphable point was -3. When -3 goes in, 0 comes out. And that should make sense, right? Because if I'm trying to evaluate the square root of x, -3 plus 3, that's just the square root of 0, which is 0. When I put in -2 here, well, the square root of -2 plus 3 is the square root of 1, and that's why the 1 was coming out. When you put in a 1 for x, the square root of 1 plus 3 is the square root of 4. That's why 2 comes out. When we found 6 to be graphable, it's because 6 plus 3 is 9, and the square root of 9 is 3. And then we also found 13 to be graphable because 13 plus 3 is 16, and the square root of 16 is just 4. So these are my graphable points: -3, 0, -2, 1, 1, 2, 6, 3, 13, 4. Remember, the graph was like this kind of sort of curve thing, and it goes on forever and ever over to the right. Which means with my domain, remember my domain, the first point I could graph in my domain happens to be this -3. So for my domain, it's a set of all x such that x is greater than or equal to -3. The range is going to be coming from that y value, and it's going to be anything that's going to be greater than or equal to that value. So y such that y is greater than or equal to 0. Those are the only points that were graphable starting from there, because once I went lower than -3, I had an error message, so I can't do those. But I could always find some point, let's say over at 11.5, that has a y corresponding value. Or I could find a point over here, let's say maybe 0.25 negative, that would have a y value. So as long as my x's are greater than or equal to -3, then I get some answers, and then my y's are always going to be greater than or equal to 0. Fill in an x coordinate for the following relation so it's not a function. Well, to not be a function, no x's can repeat. I've got a choice of these following x's, 2, -3, or 5. I'm just going to put in a 5. I could have put in a 2 or -3 as well. This one I want to fill in an x coordinate so my graph is a function. Remember, x values cannot repeat. So if these are all my different x values, and remember, x values cannot repeat to be a function. X values can not repeat. Then I'm going to pick some other number. I don't know, make it a 6. So that would actually be a function. Use the graph of the function f of x. Find f of 2. So that means evaluate the expression when x is 2. Well, when x is 2, y is this point, over 2, 1, 2, 3, 4. So f of 2 is 4. When f is negative, when x is -1, or f of -1, when I go to -1, I need to go up 1 So then f of negative 1 is 1. In other words, all that's really saying to you, come on, all that's really saying to you is if x is 2, my corresponding y value is 4. At x negative 1, my corresponding y value is 1. Remember, the answers are what's in blue, but they're just showing that those are ordered pairs. Name one interval where the function is positive. Anywhere you're positive is when you are above the x-axis. So I happen to be above the x-axis here. I happen to be above the x-axis here. There are two different intervals in which I could use. They only want me to give one. So I need to sort of figure out where that is. It's almost going to be more of an estimation. I'm going to go for the bigger interval. The bigger interval is going to be in between here and here on my x-axis. I happen to be positive. Well, I don't really know what this point is, but it looks like maybe it's like a half. I'm not sure. I'm just estimating it. So I know that my x values, to be positive, I'm starting at my smallest value of 1/2, and I'm going over to 1, 2, 3, 4, 5. My largest value is 5. Remember, at 1/2, assuming that this is 1/2, it's 1/2 comma 0. 0 is not negative or positive. And at 5, my y value is 0. Again, 0 is not negative or positive. So x, starting from the middle, from the variable, x has to be greater than 1/2. At the same time, it has to be less than 5. That's my positive interval. That's one of my positive intervals. So then the other interval ends up being the one that's over here, and it's only in between here and it's such a small interval. I can't even really kind of figure out what it's going to be, so we're not even going to worry about that one. It's the interval that's much larger that we're going to deal with. So it only says to name one. All is good. If we need to name an interval where the function is negative, then what we're looking at is stuff that's below the x-axis. Right here on below the x-axis and right in between here on below the x-axis. Either one of these seems a little bit manageable because it looks like we can find those x values. So I'm below the x-axis here, which is not quite at negative 1, and I'm below the x-axis here, which is probably about that 1/2. So we're going to basically say that somewhere in between the negative 1 and the 1/2, remember x is in this and x is in the middle, x is going to be more than negative 1 but less than 1/2, and that's where I find some stuff, a graph below the x-axis. The other one we could probably name 2 because we're below the x-axis here and here, and that's 1, 2, 3, 4, 5, and 6. So we could also say that in between 5 and 6, remember not equal to, but greater than 5 and less than 6, my function is definitely negative. Okay, we can't include those points on the ends because that's where the y value is 0, and 0 is not positive or negative. Okay, so then we look at the next one. Same graph. Name one interval where the function is increasing. So we are increasing, it looks like in a couple of places. For sure, we're increasing from here to here. Actually, we're only increasing in one place, really just from here to here along that curve. So the interval where the function's increasing. We start increasing from this value up to this value. Okay, so it's the x-coordinates that we're looking at. This x-coordinate down here happens to be 0, and this x-coordinate here happens to be 1, 2, 3. So my x-coordinates between 0 and 3, that's where I find myself increasing. Now remember, I don't want to use those turnaround points to say that's where I'm turning, that's where I'm increasing. I'm going to have it being once I start getting greater than 0 but less than 3, that's where my function starts rising. More than 0 but less than 3. If we want to talk about decreasing, my function is decreasing starting from this point down to here, and then from this point down to here. So again, we're looking for the values on the x-axis where we're decreasing. So I'm going to actually go for the bigger one. I could go for either, but I'm going to go for the bigger one. And the bigger one is decreasing starting here, which happens to be at 3 on the x-axis, and going down to here, which happens to be 4, 5, 6. So what's happening for where I'm decreasing is, again, my smallest x value where I decrease is 3. It stops decreasing at 6. That's where the graph completely stops. And then what happens here is x is going to be the value that's somewhere in between my 3, so I'm greater than 3, but I'm less than 6. That's where I'm decreasing. If you wanted to go on the other side, that's fine. I'm decreasing between this value and this value, which is really only from -1 to 0. So the other one would be that x would have to be between -1 and 0. And again, it's more than -1 where I start doing the decreasing, and it's less than 0 where I finish my decrease. How many x-intercepts are there? How many places does this graph cross the x-axis? And it happens to cross the x-axis 3 times. Here, here, and here. There are 3 of them. If we want to name one, 3 x-intercepts, and when you name them, you use an ordered pair. I'm going to do this one here, which is clearly an ordered pair, which would be 1, 2, 3, 4, 5, comma 0. How many y-intercepts are there? I only cross the y-axis once. So there's one y-intercept. It has an ordered pair of -1 or 0, comma -1. Stay at the origin and go down. Just have a few more to go. The accompanying graph shows the heart rate and beats per minute of a jogger during a 4-minute interval. So time is going across the bottom. So here's from 0 to 4 minutes. And then his heart rate, it looks like it's starting at 60 and looks like it's going up to 110. So what is the range of the jogger's heart rate? Remember, at 0 time, he actually has a heart rate. He's got beats. It's 60 beats. So anything that's 0 doesn't make sense. The interval is going to be from 60 to 110. Given the function f of x equals -x squared minus 2x plus 1, find the values of f of 3, -4, and 1/2. Show your work. So f of 3 equals -x squared minus 2x plus 1. Don't forget what's being plugged in there is a 3. When you do the order of operations, you've got to do the exponent first, which means it's 9, bring down the negative, minus 6 plus 1, -15 plus 1 is -14. When I now do f of -4, it's -x squared minus 2x plus 1. In this case, what I'm going to type in here or put in is going to be the -4 goes in for x. And then what happens is -4 squared is 16. Carry down the negative. -2 times -4 is +8 plus 1. -16 plus 8 is -8 plus 1. And what comes out is -7. And last but not least, I've got to evaluate f of 1/2, which equals -x squared minus 2x plus 1. Don't forget you're putting in -1/2. And when I evaluate this, -1/2 times itself becomes 1/4, but I have to carry down the negative. -2 times -1/2 is +1 plus 1. And what ends up happening is I'm going to be getting, you know what? I made one mistake here. Is it -1/2? I made a mistake. It's actually +1/2. So let's fix this. Sorry about that. Right, let me go back up. We're not looking for f of x to be -1/2. It's evaluating f, excuse me, of 1/2. So let's try this again. Okay, so 1/2 squared becomes 1/4, but I have to carry down the negative, so it becomes -1/4. -2 times +1/2 is -1 plus 1. It turns out that -1 plus 1 cancel out, and then f of 1/2 is -1/4. One more to go. Given the function f of x equals x squared plus 3x minus 2, now we're putting in some variables instead. When you evaluate the rule for f of a, x squared plus 3x minus 2. When a goes in, it becomes a squared plus 3a minus 2. There are no like terms. That's the end of it. Nothing I can combine there. When I evaluate the function at negative a, it becomes, again, x squared plus 3x minus 2. But I'm evaluating it for negative a. Well, a negative a times a negative a is a positive a squared. 3 times negative a is minus 3a minus 2. Looks very much like the first one, except now it becomes minus 3a, not plus 3a. And the last one is to evaluate the function at f of a plus 2. So again, this particular rule, we want to evaluate it at a plus 2. And they're asking you for x squared plus 3x minus 2. Don't forget what's going in is a plus 2. This is the one where it's more complicated because here I really have to do a plus 2 squared. Well, a plus 2 squared, if I do the box method, I can do that. A plus 2 squared. Here's a, here's positive 2, here's a, here's positive 2. This box is a squared. This box is 2a. This box is 2a. This box is 4. So a squared, or a plus 2 times a plus 2, is a squared plus 4a plus 4, plus, distribute, 3a plus 6 minus 2. Well, things that are alike, I don't have any other a squareds but that. A's, I've got 4 plus 3, so I've got plus 6a. 4 plus 3, let's try that again. So I've got plus 7a, there we go. And then I have 4 plus 6, which is 10, minus 2, and 10 minus 2 is 8. That's an 8. So to evaluate that one, a little more work, it's a squared plus 7a plus 8. All right, so that's it. Hopefully all is good, and we'll see you tomorrow.